Hello everyone, welcome to today's webinar. My name is Wyatt Pena and I'm the Vice President of Operations here at Ridgetop Group. Today I am joined by our Applications Engineer, Arshnath Carney, and one of our software engineers, Gabriella Galvin. Together we'll be presenting an in-depth look at our Sentinel Motion technology. During this session, we'll explore the capabilities of Sentinel Motion, an advanced IoT-based sensor solution designed for condition-based maintenance and prognostic health management of critical assets. The technology was originally developed nearly 15 years ago through a small business innovation research program that spanned multiple years for NASA. At the time, we were looking at faults and anomalies in helicopter gearbox systems. Our primary goal was to compare the efficacy of traditional case-mounted accelerometers versus a wireless accelerometer and temperature sensor that was machined to fit inside the gearbox. Not only did we prove the efficacy of getting an RF signal outside of a fully enclosed gearbox system, we are also able to identify a clear fault to failure progression signature and an early condition indicator or functional failure. This innovative research laid a solid foundation for our industrial IoT technology, and since then, Sentinel Motion has been adapted across multiple industries, including aerospace, energy, and railroad transportation. We greatly appreciate your participation today, and we kindly ask that you hold your questions until the end of the webinar, where we will address them during a Q&A session. Afterwards, we will be sure to provide the slides and the webinar recording to all registered attendees once it is uploaded to our YouTube channel. For today's agenda, we'll start out with a company overview, a brief introduction to and scope and background of the webinar. Then we'll cover the development history and its relationship to the IEEE 1856-2017 PHM standard. What is Sentinel Motion? The different Sentinel Motion applications that Ridgetop has been involved with over the years. The Sentinel Motion Development Kit, or SMDK, demonstration provided by our software engineer, Gabriella Galvin. And then Arsh will go over some of the future R&D that the team has been working on. And then at the end, we'll have a summary and a Q&A. Here on this slide, we have some background on our company, where Ridgetop Group is a trusted leader in the design and development of hardware, firmware, and software-based solutions for condition-based maintenance, prognostic health management, and reliability engineering applications. Our mission is to improve safety, efficiency, and operational performance for both government and commercial sectors while reducing maintenance and sustainment costs through cutting-edge innovation. We were established in the year 2000, and we are headquartered in Tucson, Arizona. We have expertise in engineering design services, circuitry for harsh environments, and advanced prognostic solutions for aerospace, defense, transportation, energy, and industrial markets. With over 2 decades of experience, Ridgetop continues to set the standard for reliability and health management solutions. We are also an AS9100D and ISO 9001 certified facility. Next, we'll provide a brief introduction and outline for the scope of today's session. To start, let's take a look at this diagram, which illustrates a conceptual approach to a prognostic health management, or PHM, framework. Today's webinar will focus on how various PHM frameworks can be integrated into a unified control and data flow structure, such as Sentinel Motion. This particular diagram was originally developed by our late colleague, James Hoffmeister, or Hoffy, and it reflects our work in advanced diagnostics and prognostics for aerospace and transportation applications. In this framework, the sensor system first acquires raw data. That data then goes through a feature extraction process, which identifies specific features linked to a potential failure mode, and from there, a prediction model analyzes feature data to provide prognostic insights. That in turn supports decision-making for fault management and health management actions. The goal is to create a validated solution that can be applied effectively for a unique customer's application. It's important to understand the relationship between PHM frameworks and the traditional reliability engineering model, often visualized by the bathtub curve. Here you can see failure rate on the y-axis and time on the x-axis. During early design and development and during the manufacturing phases, we often see high failure rates due to infant mortality issues. However, once those issues are addressed and processes are stabilized, the product or system enters its useful life stage. Over time, wear out occurs, leading to the end of the useful life. The time between detecting degradation and the point of functional or physical failure is known as the remaining useful life, or RUL, which is critical for maintenance planning. With this understanding, it's important to note that maintenance practices have evolved significantly over time. Historically, maintenance was reactive, but as we've learned more about the bathtub curve and CBM and PHM practices, there has been a clear shift towards proactive strategies. Ridgetop has been at the forefront of helping customers make this transition, developing hardware, firmware, and software-based solutions to move from reactive to proactive maintenance strategies tailored for a specific system and application. As part of this transition, there are intermediate stages such as preventative maintenance and condition-based maintenance before reaching a full PHM or predictive maintenance deployment. For example, a preventative maintenance strategy might be something like performing a scheduled oil change every 6 months, which is time-based. In contrast, condition-based maintenance uses sensor data to monitor actual degradation. As more data is gathered, this can evolve into predictive maintenance strategies where potential failures are anticipated before they occur. Over the years, Ridgetop has developed a range of tools to support this evolution, helping organizations move from basic preventative strategies to more sophisticated prognostic and PHM-based solutions. Now that we have a solid understanding of the PHM frameworks, let's introduce the Sentinel Suite family of solutions. This suite is comprised of 4 key application-specific solutions: Sentinel Motion, Sentinel Power, Sentinel Interconnect, and Sentinel IT. Each solution is tailored to a different application area, and they utilize distinct feature data types and reasoning methods to assess degradation and provide a prognostic evaluation for specific failure modes of interest. For today's webinar, we'll focus on Sentinel Motion, which is a product line designed to monitor the electromechanical failure modes in systems such as aircraft, infrastructure, wind turbines, and other critical equipment. The main goal of this technology is to prevent unexpected downtime by providing real-time diagnostics and prognostics to support better maintenance decisions. Now, if we look at Sentinel Suite and Sentinel Motion in a broader context of transitioning from condition-based maintenance or CBM to a full PHM ecosystem, this process begins with the need to communicate PHM data to a centralized platform. For instance, in this example, we're seeing how PHM data from an aircraft system is fed into the Sentinel Suite platform. This integration enables us to determine the real-time state of health and calculate the remaining useful life of certain line replaceable units or system-level components. With this real-time information, organizations can take proactive CBM and PHM actions. These actions might include optimizing inventory levels, scheduling part replacements, or organizing maintenance and services for line replaceable units. In more advanced cases, when control logic and health management are integrated into the system, automated actions can be taken to optimize performance based on mission requirements, duty cycles, or specific operational use cases. This ability to automate and integrate health management within the system is critical for reducing downtime, increasing operational efficiency, and minimizing costs, especially in complex environments like aerospace, wind, and energy. By leveraging solutions like Sentinel Motion, we are able to help our customers move from reactive maintenance approaches to predictive, data-driven maintenance strategies, driving significant improvements in operational readiness. So as we move forward in today's session, we will dive deeper into Sentinel Motion, exploring how it works and the different types of data it captures and how it helps organizations prevent failure modes in critical assets and improve overall system reliability. Now let's take a look at some of the development history and how our technology aligns with the IEEE 1856-2017 PHM standard. Between 2009 and 2015, the foundation for this technology was laid out through the NASA SBR program that I mentioned earlier, where we focused on failure modes in helicopter gearbox systems. At this time, this was really before the term IoT became a widely recognized term as it is today. We were comparing the performance of an embedded accelerometer against traditional case-mounted accelerometers, which was an effort that hadn't been done previously, especially in a metal gearbox system where it is very difficult to get an RF signal out of such system. Despite these challenges, we succeeded and we proved it was not only feasible, but also that we were able to extract a fault to failure progression signature by looking at the time sequence averaging signal for a cracked gear tooth. The testing for this was conducted at the NASA Glenn Research Center using the transmission gearbox of a Bell Kiowa helicopter. This diagram, you can see where our RotoSense smart sensor was embedded in the gearbox system. The sensor housing seen in the upper right corner was custom machined out of aluminum to fit within the transmission gearbox. We later expanded this to work in other failure modes and look at such as the planetary gearbox system or rotating axles and torque. By focusing on extracting relevant condition indicators in these different locations, we're able to identify the data acquisition and fault to failure progression signatures for different failure modes. Once data was captured, it was transmitted back to a centralized gateway system, which handled both the data acquisition and offloading for post-processing and analysis. To quickly summarize the results of that research, the technology performed exceptionally well during testing, with over 113 hours of continuous operation in a highly accelerated live test or HALT test. And during these tests, it included operating speeds of up to 6,000 RPM, and RotoSense captured just as much data as 5 of the case-mounted accelerometers with a very high sample rate and offering continuous transmission of the accelerometer data. The key takeaway was that we were able to successfully extract the failure mode across all 3 axes being monitored, and the TSA, or time sequence averaging signal, proved as a useful feature data extraction technique and a prognostic assessment for the cracked gear tooth fault. These results were published in a white paper covering the evolution of the MEMS-based wireless accelerometer sensors, and then following that, there was a NASA spin-off article for how we adapted this technology for the railroad industry. Since 2015, we've made significant progress in applying this technology to other industrial IoT applications. Here are some key publications that document how we hardened this design, working closely with railroad and railcar manufacturers. We tested the sensors in extreme vibration and temperature conditions, as well as other environmental stress factors adhering to IEC standards. As a result, the sensors were qualified to withstand continuous vibration levels up to 100 Gs across a range of different frequencies. Our ongoing research in collaboration with different universities and through our own Ridgetop laboratory has led us to take this technology from being a useful R&D tool to a field-tested and deployed solution. In particular, we've been working with small-scale pilot studies in the railroad industry and have helped short-line railroad operators understand bearing degradation and track geometry issues. These studies have enabled operators to gather data and transition toward condition-based maintenance and prognostic health management of critical assets and their failure modes, which we'll touch on further in this presentation. So how does all this relate to the IEEE 1856-2017 PHM standard? Our technology was developed with a clear understanding of the PHM frameworks and its core operational processes. Recently, we redesigned the technology to be organized specifically around these core operational processes. It begins with sensing and data acquisition, followed by data manipulation through edge computing or post-processing. And from there, we move to state detection, health assessment, and prognostic assessment, which involves various analysis methods to evaluate performance and degradation for specific failure modes. Once a robust understanding of these failure modes is developed along with a fault library, we can generate actionable advisories and perform health management actions. This is fully integrated into our Sentinel Motion View software platform, completing the evolution from a useful research tool to a comprehensive PHM system-level solution. At this point, I'd like to turn it over to Arshnath Carney, who will walk you through an introduction to Sentinel Motion. We'll first start out with a brief introduction video. right. So, yep, I'll transition it over now to Arshnath Carney.
Hello, everyone. Let's go ahead and take a look at what is Sentinel Motion first. So Sentinel Motion is a technology designed to focus on remote asset monitoring and management using acceleration, temperature, gyration, GPS, and any other custom data stream from mission critical equipment. As Wyatt said earlier, Sentinel Motion is fully compliant with 1856-2017 PHM standard that's set by IEEE, and it mostly comprises three elements that are fully IoT connected. So on the deployment diagram that highlights the train deployment here to the right, the first element is a smart sensor, smart IoT sensor, or a wireless network of multiple of these. The one we manufacture here is called RotoSense, but Sentinel Motion can also work with any custom IoT-enabled sensor. Moving on to the right, the black box that you see there is called the Sentinel Gateway, and it's used for communication and data management and interfaces with the RotoSense or custom IoT sensors, as well as if we move on one more to the right, the Sentinel Motion View software package, which is used to communicate with the gateway as well as interact and control the sensors. Sentinel Motion is a customizable modular technology for different end user applications as well as different market sectors. So what are RotoSense smart sensors? RotoSense is basically an advanced wireless IoT sensor that is tailored for harsh environments like railroads, aerospace, transportation, or industrial. It's housed within a robust assembly and features a triaxial accelerometer with an impressive 200G sensing range. It's also able to extract high resolution acceleration, temperature, and gyration signatures that are oftentimes caused by gear faults, stresses, and other machinery faults. Um, Regardless of what it's being used for, all sensors have a 16-bit ADC resolution, programmable sample rates from 1 hertz all the way up to 100 kilohertz, um, and adaptable acceleration ranges. Shown here to the right are different form factors for RotoSense, with RotoSense 1000 being the earliest iteration, all the way down to RotoSense Series 3000, which is currently being used for deployments. Now we have the sensor part, but we need something to collect the sensor data and manage all that. So for that, we have the Sentinel Gateway. It is an IoT communications device and data management hub that brings edge computing to applications where your smart sensor networks deployed. Um, when combined with Ridgetop's RotoSense or any custom smart sensors, the gateway provides the end user a complete data acquisition and management toolbox, along with asset monitoring and management functionalities too. The gateway has a Linux-based single board computer at the core. You can access it using Ethernet, cellular, and dual-band Wi-Fi. It also offers a secure access point and network drive for all log data. We also have a 1 terabyte SSD for local data storage, a dead reckoning GPS module for the GPS data stream, which is used to correlate to the acceleration sensor data. And lastly, the gateway stores, or rather hosts the Sentinel Motion View software application. So Sentinel Motion View, which we will take a deeper dive into here in a few slides is the primary graphic user interface GUI and that interacts with the gateway and the RotoSense or the custom IoT smart sensor network. The software is hosted locally on the secure network drive on the gateway, and it provides visual representations of data and other key information originating from the smart sensor network. It also provides actionable insights and decision making for the smart sensor and gateway network tree. Um, End users who want to integrate acquired and monitored data from Sentinel Motion View within their own systems or systems of systems can do so by downloading these files in TXT or CSV formats, or by utilizing the Sentinel Motion View API for cross-platform data export. Um, Sentinel Motion View is cross-compatible on a variety of browsers like Edge, Mozilla Firefox, Safari, and so on. And it's also accessible on desktop, tablet, as well as any mobile device. Now we'll go ahead and look at some of the applications of this technology. Shown here to the right is a map of the main market segments that Sentinel Motion currently services. And there is also a detailed list to the left with the segments more detailed out. So we mostly use Sentinel Motion in the rail transportation industry, where we are detecting wheel and bearing defects and also monitoring the condition of the track to reduce derailments. Likewise, it can also be used in aerospace and aviation for harsh environments up to 100G, and the smart sensors RotoSense are flight qualified for such environments. We also use Sentinel Motion in the energy and industrial sectors, where we try to avoid costly breakdowns and have to monitor remote assets in remote locations. Specifically today, we'll take a deeper dive into Sentinel Motion for rail. Now, let's take a look at some of the major challenges the railroad industry faces today. First, there are a number of common problems that can affect the safety and efficiency of rail transportation. These include mechanical failures of railroad vehicles or their components, frequent derailments, and poor ride quality. We also face environmental and weather-related issues that can disrupt operations, such as extreme temperatures, floods, and snow. Communication and signaling failures pose a risk to safe railroad management, while infrastructure deterioration continues to be a pressing issue. Lastly, improper loading and securing of cargo can also lead to accidents or delays. But what are the root causes of these problems that were discussed above? They can be traced back to several key factors: broken rails or welds, failed bearings, and defective wheels. There's also unusual track interaction, which can be exacerbated by aging infrastructure. Think about friction wear and track deterioration. Human factors also play a role. Errors by operators, such as excessive speeds or overworked crews, are a significant concern. Additionally, poor maintenance, track geometry, and extreme weather conditions like floods or snow often contribute to the issues faced by the industry. For example, look at the 2023 Norfolk Southern derailment in Alabama that's shown in the top right here. Another significant derailment was in 2024 on the Lehigh River when three train cars collided and crashed. In addition to these cases shown here, we must also acknowledge the East Palestine derailment, which happened earlier this year and drew widespread attention. This incident was caused by a temperature rise in one of the bearings, which the hotbox detector wasn't able to catch. This incident exposed the dangers of chemical spills from rail incidents, leading to health and environmental concerns. The aftermath of East Palestine continues to influence discussions on railroad safety and infrastructure investments. From these kinds of issues, it is clear and evident that we need more of these remote asset monitoring solutions like Sentinel Motion. So currently in the railroad industry, they use mostly traditional maintenance practices, which are wayside detection equipment, such as your hotbox detectors that we talked about just now, and the wheel impact load detectors. Also, there's more so visual inspection and written reports, work order requests, and then interval-based maintenance. Most of this happens in the reactive maintenance realm, and it can prove to be very expensive. So to solve this problem, in as of today, there's emerging technologies and solutions like big data analytics. Machine learning is a big one. Forecasting and advanced modeling, IoT sensing, and sending inspection vehicles at the track, the part of the track them itself is a big one. Next. So So when we got into the railroad industry in 2015, Ridgetop tested Sentinel Motion as a part of a FRA R&D program at the Transportation Technology Center Inc., now MXV Rail, in 2015 on their high tonnage loop. The original RotoSense design from the NASA project that I talked about was integrated into industrial wheel hub sensor design that is shown on the right here. The main testing objectives were to characterize track infrastructure, which is also to geolocate track features, to detect track anomalies such as broken welds, and to detect faults in wheels, hubs, and bearings. So Ridgetop found that Sentinel Motion was a viable IoT solutions for such railroad harsh environments. We were also able to detect common track features such as turnouts, welds, concrete, and steel bridges, also crib ties. And then Sentinel Motion was found to be a scalable solution for remote asset monitoring and diagnostics and prognostics of track, wheel, and bearings. Next. So shown here is some of that testing data. You can see the GPS and acceleration data correlated to the track features. So the GPS data almost shows a perfect loop as seen in the track diagram to the bottom left. Also, we have the vibration data to the top right, in which we identify the different track features from the table 3 just below it. Next. As of today, Ridgetop and Innovative Operations Technology, IoT, are currently collaborating on a joint pilot study program with Reading, Blue Mountain, and Northern Railroad in Port Clinton, Pennsylvania. This is where the latest design upgrades to Sentinel Motion for rail are being tested and evaluated. The main testing objectives here are to verify that the SNR has improved since the TTCI testing to verify wireless and cellular communication in remote scenarios, to verify the use of new and different sensor operating modes, to verify new software capabilities, for Sentinel Motion view, to geolocate and this time generate a profile library for different track features, and to compare data observability at the bogey frame and at the wheel hub. Ridgetop has also been working on a vibration-based energy harvesting system that will self-power the RotoSense smart sensors. So we also intend to verify the long-term operational capability of this system. Next. Now we'll go ahead and take a look at the Sentinel Motion View GUI and it's working here through a short video. Next.
Welcome to today's demonstration of Sentinel Motion View. Today we'll showcase the latest features and enhancements designed to not only collect and analyze data, but to actively monitor and manage the health of your assets in real time. While today we'll focus on railroad applications, monitoring critical components like wheel bearings to prevent derailments, this tool is versatile and can be tailored to any system where vibrational data plays a key role. Let's dive into how this all-in-one solution works. Starting with our platform's dashboard, here you can see a comprehensive view of all of your connected assets and their related telemetry data. Cellular connectivity and additional user-defined data can be viewed for each connected deployment and the sensors associated with it. Down below, you'll find recent alerts and overall system health available at a glance, but we'll take a deeper look at that section later. Moving on to the Data Acquisition tab. Here we can manage our gateway settings and view any connected sensors. By selecting an asset, we can start data collection, view live vibrational graphs, and schedule data collections, allowing for real-time monitoring of the asset's conditions. In this case, we have vibration readings coming in from our RotoSense sensor. Using the Halt toolbox, you can easily schedule data collection from sensors attached to critical components like wheel bearings. For example, in the railroad industry, monitoring wheel bearings for abnormalities can mean the difference between a smooth operation and a potential derailment. With Halt, you can schedule data collections at precise intervals, either as a burst to capture high-stress moments during acceleration or braking, or as a continuous stream when trains are in motion. This data can be collected at specific sampling rates based on the needs of your fleet, ensuring that any early signs of wear or overheating are detected before they lead to critical failure. Sentinel Motion View goes beyond just collecting raw data. Using feature data algorithms, we can convert this information into actionable insights. For example, the vibration data is processed to identify key indicators of potential issues, such as excessive vibration patterns, and generate a feature set that can be used for further analysis. Once we have the processed data, it's available to use as an input for our embedded Adaptive Remaining Useful Life Estimator, or ARUL. This proprietary tool uses historical data and predictive algorithms to provide an accurate forecast of the asset's remaining operational time before maintenance or failure is expected. Simply create a node definition file and a system definition file, and ARUL takes care of the rest, giving you fault to failure progression signatures and other key prognostic quantities such as state of health, remaining useful life, and prognostic horizon. One of the powerful features of our platform is the ability to automate the entire monitoring and alerting process into a single seamless workflow. With just a few simple steps, a fault definition can be created defining which asset or node to monitor, such as a specific wheel bearing, and every time data is collected for that asset, the system will automatically trigger a sequence of actions. First, the data goes through our feature data extraction process, where user-defined feature datasets are identified and extracted. Next, it runs through ARUL to assess the asset's health. Finally, the system checks the FFP signature of the ARUL analysis against the predefined thresholds. If the FFP signature meets any of the defined thresholds, informational, warning, or critical, the platform instantly generates an alert notifying you in real time so that you can take proactive action. This automation enables you to combine all aspects of monitoring, analysis, and alerts into one streamlined process, ensuring that potential issues are identified and addressed before they become critical. Which leads me to our final tab, the Health Management tab. Here you can see how a service ticket is created and assigned, complete with all relevant data, including the affected asset, the issue type, and the recommended action. This keeps your asset management and maintenance processes organized and efficient. As you've seen, Sentinel Motion View provides a comprehensive, all-in-one platform for managing your assets' health. By seamlessly integrating sensor data collection, advanced analysis, remaining useful life estimations, automated alerts, and service ticket generation, this solution enables you to proactively monitor and maintain your assets from a single streamlined system. With Sentinel Motion View, you can stay ahead of potential failures, reduce downtime, and maximize the lifespan of your assets.
So that was a great technology demonstration video there, but where do we go from there into the future here? So let's go ahead and talk about some of the future R&D efforts here that are going to take place at Ridgetop. Next. So firstly, we are looking at the addition of gear and bearing specific features from Sim et al. Into the FDEP toolbox, the feature data extraction and pre-processing toolbox that was highlighted in the video previously. So in terms of some of the gear specific features, we're looking at FM0, SCR, NA4, NB4, FM4, M6A, M8A, and the ER. Within these, FM0 detects changes in gear engagement patterns as an indicator of the gear's main fault. NA4 detects the progress of defects in gears. FM4 gives you the kurtosis of the difference signal, and M6A and M8A detect surface damage on machinery components. Now, how this is all done from your raw data is shown in the diagram below. As far as bearing specific features go, we have the BPFO, BPFI, and BSF, ball pass frequency of outer race, ball pass frequency of inner race, and ball spin frequency. And again, how that is done from your acquired raw data is shown in the diagram below. Next. We will also be implementing gear local fault diagnostic techniques from Azimi et al. This was a comparative study on using a wireless shaft-mounted versus bearing-mounted accelerometer, specifically looking at geared systems. It explores techniques such as TSA, order tracking, and continuous wavelet transform to extract key features and improve signal quality under fluctuating load speed conditions. Some of the benefits of this study were enhanced fault detection sensitivity, where the shaft-mounted accelerometer captures more detailed signal and improves the early detection of local faults. We also have the directional measurement flexibility, as you can collect vibration data tangentially, longitudinally, and transversally. Techniques like TSA and CWT also help with noise reduction. And then the shaft-mounted accelerometer also effectively identifies faults under different load speed conditions. This approach can also be applied to other machinery, not just gears, and bearing shafts and turbines are some examples. So shown here to the right is a diagram of isolation of the gear fault and its visualization for different fault scenarios, where you can see the heat map of where the fault actually occurs as compared to its true known occurring position. And shown below is the in-house test bed that was used here at Ridgetop to conduct this study. Next. Lastly, some other enhancements include we want to create a library of failure modes. So conducting halt testing for different components like axles, bearings, and wheels. and building a comprehensive database for performing prognostics. We also want to incorporate additional data streams such as fuel consumption, brake temperature, ambient conditions like temperature and humidity, train load and cargo, and then voltage and current, especially moving forward for electric trains. Um, we also plan on implementing multivariate analysis through Ridgetop's 14 MVA algorithms that use multiple sensor data streams together and detect patterns and correlation indicative of wear and damage. Lastly, we also want to use machine learning, specifically ensemble learning, transfer learning, and then CNNs for spatial anomaly detection, like identifying wear patterns from track inspection data, and RNNs in the case of a regular vibration or sensor data. Next. So in summary, today we introduced Sentinel Motion and its development history. We highlighted the innovative IoT-based monitoring solution and took you down its development lane over the past decade and its alignment with the IEEE 1856-2017 PHM standard. So Sentinel Motion provides real-time monitoring of mission-critical equipment. It enhances safety through anomaly detection and predictive maintenance, and it is a cost-effective, scalable solution for CBM and PHM applications. We also showcase a live demonstration through a video for the SMDK, the Sentinel Motion Development Kit, and its intuitive graphical user interface, the Sentinel Motion View. Lastly, we provided a glimpse into ongoing innovations and enhancements for Sentinel Motion's capability across different industries and sectors. Next.
Awesome. Thank you, Arsh. That was a really good introduction and background information on Sentinel Motion and some of our ongoing and continued work. So we would again like to thank everybody for their participation in today's webinar, and we'd like to open up the floor for any questions. And I did see a few questions come in through the chat, so I'll go ahead and get those addressed. So the first question that we're seeing is, what types of machine learning and AI methods are planned to be implemented, and under what segment of the software would they be implemented? So, Arsh, do you want to go ahead and take that question?
Sure. So as far as machine learning goes, if you go to the slide, 2 slides behind, yeah, we want to use multiple models to combine predictions, and that'll ensure a more accurate fault diagnosis in railroad systems. We also want to look at transfer learning, which involves pre-training models on simulated railroad data, and then sort of fine-tuning them with the real-world data. And as I talked about before, look at neural networks, convolutional for images that will be provided or taken through the track inspection, and recurrent for your usual vibration or acceleration or gyroscope sensor data, as well as any other end user custom data stream.
Yep, excellent. I think one more note on that as well is, with our access to longer term aging data and in our different applications, right, we're going to be able to also apply some big data analytic tools towards extracting the efficacy of different prediction algorithms and based on different types of feature data. So as we look at the different types of feature data and their efficacy of understanding that failure mode, which one gives us the earliest sign of an impending failure mode is something, we want to continue to study. So AI, machine learning, and even the multivariate analysis algorithms, we know are going to be playing a key role in that for our different applications. So another question in the chat is whether or not the different form factors of RotoSense are commercially available, or how can a custom form factor be designed. So I could go ahead and take this question, and this is something we get asked a lot during technology introduction meetings. So Ridgetop Group does offer a number of different engineering design services for hardware, firmware, and software development. And an important note about the different RotoSense form factors is we customize these for very specific applications. So whether it's a particular bearing or housing design, we're able to do that. But an important aspect is all of the firmware and software elements stay the same. So adjusting the layout and accelerometer or different types of data for different specifications, we're able to customize those into different form factors for a unique customer application or use case. So we're happy to do that, and the technology is available through the Sentinel Motion Development Kit, or SMDK, and we work with different research collaborators and technology integrators on a global scale. So if you have any questions about custom design and deployment options, definitely feel free to reach out to us or our sales representative network on our website. All right, and I think that was our last question for today, but I would encourage any of our viewers on our YouTube channel to reach out via email, and we'll be glad to get in touch. So we're always happy to explore new projects and opportunities, and we look forward to talking with you about how Sentinel Motion can support your industrial IoT deployment and use case. Thank you, everybody.